In the previous video, we prepared this linear layer, and as far as I remember, the last step, it's right over here. We add to the output the bias term from the linear layer. But we have implementation for the matrix multiplication, but for the plus sign, we don't have any addition implementation. So it means that we need to implement this operation. Gradients must be correctly propagated across dimensions that may be different between tensors. And basically NumPy supports and allows tensor of different shapes to interact. And this mechanism it calls the broadcasting. I have a small example for you. We have matrix A with shapes 3 times 1. It means that we have 3 rows and 1 column. Matrix B with 1 row and 4 columns. And we perform the broadcasting addition. And in the result, you can see it looks like this, yeah? So the broadcasting basically stretch the dimensionality of matrix A to 4 items in the column dimensions of matrix B and stretch the dimensions of the rows of the matrix B to 4 items to match the dimensions of the rows of the matrix A. So and then just performs the addition operation, and result shape is 3 times 4. I have a video about the broadcasting and matrix multiplication rules. You can check it. And our purpose is to handle the gradient backward propagation by summing over the extra dimensions created by broadcasting. I decided to implement this backward broadcast method as the high order function that carry the tensor argument to the backward step. Inside the backward broadcast, we build the backward method, backward function that receives the gradient argument. And during the computation in the backward mode, we can just carry this tensor and use the backward for the backward computations. First step, if tensor and dimensions equals 0, it means that we are working with the scalar, and in this case we need to call return numpy sum, and we sum the gradient up because we need to shrink the dimensionality of the tensor to scalar value, and we sum everything up and return scalar 1 item from this tensor. The second case, if the gradient number dimensions equals 0, it means that we are working with the scalar value and we need to return the gradient. For the next steps, let's consider 2 examples to modulate what's really going on for the backward mode. And I have first basic scenario that we will cover. It's right over here. We have tensor A with shape 2 times 2. Yeah, it's just 2 times 2 matrix. And the tensor B with the shape, it's just only scalar inside. Yeah, shape is just only 1. And when we run the sum between the tensor A and the tensor B, we just stretch the tensor B to the dimensionality of the tensor A, 2 times 2. So it means that when we will compute the gradient, we start from the point where the tensor C is 2 by 2. Let's, for example, modulate the gradient C as the matrix full set of ones with the dimensionality 2 times 2. Yeah, and it's just numpy once like tensor C. And when we go backward, and you need to remember that we have the sum operation that contributes basically nothing to the future computation in the gradient, in the backward mode, because it's just sum, yeah, and basically it makes no changes in the backward mode. And what we need to do is to assign as the gradient of A the gradient C. Yeah, we just spread backward this basic gradient. But for the matrix B, for the tensor B, it won't work by this way, because the tensor B is just a scalar. And it means that we need to shrink the dimensionality of the gradient to match with the exact shape of the tensor B. And you can see how it works. Yeah, we sum up the gradient C, because we goes backward. Yeah, we take this gradient C that we spread backward in our gradient graph and sum across the dimensions that we extended. And we extended the dimension 0 and dimension 1. And we don't need any, like, we can switch this flag, keep dimensions to false, because basically we shouldn't preserve the same data structure for the gradient, yeah, because we just we removed one of the dimensionality. So, and it means that we just need to provide the axis where we need to shrink the tensor and install the skip dimensions flag to false. And you can see the result of this computation. Yeah, we have gradient B, it's just the scalar, yeah, because we sum up all of the dimensions, yeah, across these two directions. As the step number 1, we need to calculate the number of dimensions that we added to the tensor to achieve the exact gradient shape. And we can add number dimensions variable added. And let's make it by this way. We need to subtract from the gradient number dimensions the original number of dimensions of our tensor, and we just subtract the original dimensionality to compute this prepended dimensions, yeah, and we can use the mean between 0 and this computation, yeah, because in case if we have something very strange like negative value, we just return 0. So, and if if the number of added more than 0, we can change the gradient like this, gradient sum, and as far as I remember, what we what we have done here, we just add axis that we sum. So here we need to do something similar, yeah, we need to provide an axis. We can use the tuple, and then let's define the range for the number of added dimensions. And we know that keep dimensions should be false, because we just compute this prependent dimensions and then just drop them, just shrink the dimensionality of the gradient with this sum operation, yeah, to condense the data in the right axis. But we have one more scenario. When the tensor B has shape 2 times 1, so we already have this axis, but this axis just don't match, yeah, this axis don't match, and in this case we need to extend, yeah, just broadcasting, just extend, just add one more, just copy this vector along the axis. And we have the same action, we have sum, then we just build the tensor. We, in this case, assign the same gradient for the tensor A, because we have no any changes during the broadcasting for this tensor. But for the tensor B, we need to compute the gradient and add the axis that we added with the keep dimension true flag activated. We need to sum the selected, the chosen dimension that we just extend. We copy the data. We just extend the dimensionality of the original tensor, and in this case we need just to sum along this axis all of the vectors. And you can see how it looks, what is the result. We have this result of the computation, tensor C, and we have gradient C. We copy this gradient C for the gradient A, and for the gradient B, we sum the gradient C along the axis 1. So we can program the same for our backward broadcast. We need to add reduce axis. So let's define it as the tuple, and then we can iterate through all of the dimensions in our original tensor, because we need to find the dimensions that we extended. So for dim in range, and let's add these dimensions, and we need to add the condition. So we need to follow the example. So if the original tensor dimension equals 1, so if the tensor dot shape dimension equals 1 and the gradient shape dimension more than 1, it means that we extended this dimension, and we need to sum along this axis but keep the dimensionality of the original tensor. So, and if we find such axis, we need to change the gradient to gradient dot sum. We sum along the reduce axis, so axis, reduce axis, and keep dimensions true. So we need to just sum up along these dimensions, and as the last step we need to be sure that if the gradient dot shape after this transformations didn't match with the tensor shape, in this case we can use the gradient reshape and use the tensor dot shape as the original shape that we need to follow for the gradient. And of course, after all of this we need to return the gradient, and I think that this is the implementation that we need. Okay, and let's copy and just create the static method inside the tensor class. Let's do this, let's say after the matrix multiplication. Static method. Okay, let's align. Okay, good. Okay, now we are ready to implement add method and sub, because now we have everything that we need. And you can see how the addition works. We have two tensors and we just sum them up. And the derivative of such operation, we just follow the basic calculus, yeah? Derivative of this operation with respect to A equals 1, and derivative with respect to B equals 1, yeah? So, and it means that we need just to follow the broadcasting rules, and that's everything that we need, yeah? This operation contributes to the gradient graph nothing, basically. Let's add the method add, and we have tensor A as the tensor. The second term, it's the tensor B, and we need to return the tensor back. Okay. As the first step, let's perform the output. A data plus B data. It's our data output. As the second step, we need to define the requires gradient, and we have A requires gradient flag, or the B requires gradient flag. If any of the leaves of this operation, yeah, any of the tensor requires gradient, we just switch on the gradient to the computational graph. Okay, and dependencies as the list. So if the A requires gradient, we need to add to the dependencies list, append the leaf, and as the value we use the tensor A, and as the gradient function we can call the tensor dot backward broadcast the tensor A. And as far as I remember, we just carry this tensor argument, this A, and it returns for us back this backward action, that will work inside the computational graph during the backward stage. Okay, and we need to do the same if B requires gradient, dependencies, append, we need to add leaf, but value B, and gradient function tensor backward broadcast gradient for the tensor B. Okay, last step, we need to return the tensor data output requires gradient and the dependencies list. So I think that this is the implementation for the add operation inside our tensor. Okay, and I think that we can use this add method as the static method. Let's put it right over here, static method. And we are ready to move on. We need to overload the add action. We have self as the first argument and other as the data. We return back the tensor data type. Okay, and we need to return tensor dot add, and we use self, and as the second argument, as far as I remember, we have the data gate, tensor dot data gate, and we wrap by the data gate this other data. And right now we activated this add action for the tensor. It means that our linear layer right now, we have everything that we need. Everything should work fine, because this action plus we overloaded inside the tensor class this operator, and right now we have dot product and we have the plus sign. But we can't stop here, yeah? We now just completed the implementation of the linear layer, and we are ready to add more operations, because it's absolutely necessary to implement the most important operations that we will use to build the training loop with our tensor class.